Hello everyone, welcome to A plus BI. This channel is all about complex numbers, and in this video we're going to be solving a nice exponential, I'd like to say, but it's not exponential, kind of like a power type of equation where we have z to the power I equals e to the power negative pi over 2, and we're going to be solving for z because I is a constant, as you know. If you didn't know that, let me tell you, I is the square root of -1 because I always forget to talk about it, and I squared is -1, obviously, by this. I say the square root because -1 has two square roots, but this is considered the principal square root of -1. So we're kind of going outside the real world. If you like the real world and trigonometry, algebra, number theory problems, go ahead and check out CyberMath, my other channel, my very first channel. Maybe that's where you came from. Anyways, let's go ahead and take a look at this equation because I think it's pretty interesting. And if you've seen my previous videos, you'll know what I'm talking about. If you're new to complex numbers, go ahead and check out my lecture videos and ask a lot of questions. All right, so we have this equation where we raise a complex number to another complex power and we get a real number. How is that possible, right? Isn't that amazing? The world of complex numbers is actually quite amazing. And that's why we're here to explore, okay? So we have something called an exponential, right? So we're going to do a complex exponential here. By definition, z to the power w can be written as e to the power w ln z. If you think about it, kind of bring this here. That becomes e to the power ln z to the w. And by definition, e to the power ln something is something. So this becomes z to the power w. But by definition, we have this. This is something that you can always use with complex exponentials. Why? Because when the base is a complex number, how do you define it? Like, what does 1 plus I to the power 1 plus I mean, right? Well, I made some videos about these. You hopefully know what it means. But to make it better looking, we can use the exponential function. So when the base is e, we do know that we're dealing with some type of exponential. And also, we have w multiplied by ln z, the logarithm of a complex number. That's called the complex logarithm. Let's go ahead and define that as well. And to define it, we're going to use the absolute value of a complex number and the argument of a complex number. And the argument is basically if you plot a complex number in the complex plane, which is also called the argand plane, you're going to get an angle like theta. And if this is z, like a point or what do you call it? A vector, however you want to define it, you'll get an angle and z will be the dot or the point with the coordinates. Theta is going to be the angle measured in the positive direction, which is counterclockwise. And theta is called the argument of z. Of course, z has infinitely many arguments because you're allowed to add multiples of 2 pi to this. So this means we're going to go with the principal argument for this case so that it's going to be between negative pi and pi, and it's the smallest possible angle. Okay, great. Now, let's go ahead and use this information to simplify our expression, okay? So z to the I, by this definition, w is I. In this case, it's going to be e to the power w times ln I. So how do you find ln I by using this definition? Well, easy. If you replace z with I here, they kind of switch roles. Z is the base, but now the exponent. So ln absolute value of I plus I times the argument of I. What's the argument of I? If you plot I in the complex plane, you're going to realize that it is 0 plus I, or 0, 1. Therefore, it'll make an angle of pi over 2 radians because it's a rotation, basically. So this is 1, the distance from 0, obviously. So ln 1 is 0 because this is a real valued ln. And argument of I, at least the principal argument of I, is pi over 2. So ln I can be written. This is one way to write it. Of course, there are infinitely many ways. You can add multiples of 2 pi to it. But I'm talking about one way to write it is going to be I times pi over 2. In other words, this is kind of interesting because ln I divided by I is a real number. Or I divided by ln I is also a real number. So if you get a problem like z divided by ln z is a real number, then you might think, okay, this is probably I or something like that. Anyways, does this work with 2i? That's for you to find out. Now, let's go ahead and go back to our original problem. Z to the I is equal to e to the power negative pi over 2. Uh-oh, pi over 2 came up again. Now, we're going to replace z to the I with e to the power I ln z, right? And then that is going to give us, what am I talking about? Okay, here we go. E to the power I ln z equals e to the power negative pi over 2. Did I say ln I? Wait, z to the I is e to the power I ln z. This is interesting. I don't know why I wrote it this way. That's funny. Okay, I'm probably confusing myself. I don't think I'm going to need ln I, am I? I don't think so. Okay, so we're not going to need ln I. Sorry about that. I don't know why I got into this. This was probably be appropriate for something like I to the power z. Anyways, that's a different problem. We'll talk about it later. Let's get back to this. Okay, so here we actually get the ln of z from this equation, right? So by setting these equal to each other. By the way, I got to tell you, e to the power 2 pi ni is another way to write 1, okay, in the complex world. Why? Because 2 pi n is a multiple of 2 pi, and if your angle is a multiple of 2 pi, you're always going to be getting 1 on the unit circle. Of course, we're talking about a number whose modulus is 1. Modulus is absolute value, by the way. So this gives us I ln z equals negative pi over 2 plus 2 pi n I. So you're allowed to add that, and this is going to give us more solutions. The next step, a lot of people are going to divide by I or multiply by I, but I like to multiply by negative I. Why? Because negative I squared is 1. So if you multiply both sides by negative I, I mean the whole thing, you get negative I squared, which is 1. That's ln z. These two negatives will make a positive, so I pi over 2. And then this will become negative I squared again, so plus 2 pi n. And then this part is actually going to be pretty interesting. Remember, we got to find z, and z is e to the power ln z, right? We have that identity even for complex numbers. So we can go ahead and plug it in. E to the power I pi over 2 plus 2 pi n. Wait a minute, is that the final answer? We can simplify this. Let's go ahead and split it up. Write it as e to the power I pi over 2 times e to the power 2 pi n. You got to remember that this is actually a real number, right? This is a real number, but this is not. This is an exponential, and Euler told us that e to the power I theta can be written as cosine theta plus I sine theta. What happens if theta is pi over 2? Then you get e to the power I pi over 2 equals cosine pi over 2 plus I sine pi over 2, but sine pi over 2 is 1, and this is 0, so you get I from here. In other words, e to the I pi over 2 is I because the argument of I is pi over 2. Does that make sense? I hope it does. So this is I, and this is a real number, so z, the solutions can be written as e to the power 2 pi n multiplied by I. And n is an integer, of course, right? It can be negative or positive, and we get the general solution this way. But wait a minute, what happens if n is equal to 0, right? Then you get z equals I, and of course this works because I to the power I is e to the power negative pi over 2, and I made a video about this before. Go ahead and check it out. And this brings us to the end of this video. Thanks for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe, take care, and bye-bye.